So one of the themes that many have touched upon is that it takes a lot of work to verify AI-generated proofs. And so one such approach which people have put forward is to pair AI with formal verification, such as the lean programming language. And to speak on that, we are very happy to have our final speaker for the day, Carina Hong. She's the founder and CEO of Axiom Math, which is an AI company building a self-improving, super intelligent reasoner, starting with an AI mathematician. Uh, there is some echo. Sorry.
Probably me.
Sorry, just one second. Yeah. So to say a little bit about Carina, so she was a Rhodes Scholar at Oxford. She earned a master's in neuroscience and did deep learning research at UCL Gatsby unit. She was a math and physics undergrad at MIT, where she has done a lot of work, research work spanning number theory, combinatorics, and probability. And she won the Morgan Prize, which is considered the highest honor for undergraduate math research, and the AWM Schaefer Prize, which is awarded to an undergraduate woman in North America. So yeah, unfortunately, Carina couldn't make it in person. She wanted to, but we are happy that she can present virtually. Yeah, thank you, Carina.
Can you hear me?
Yeah, we can hear you.
Okay, perfect. I'm going to share screen. There might be an infinity error, so let's see how it goes. Can you see this one slide?
Yeah, we can see.
Okay, perfect. Hi everyone. I see already in the audience there are some of my old friends. So hi to Mark, hi to Bryce. Yeah, thank you so much for the organizers for inviting me to speak. Today I'm going to probably cover a little bit more about what's beyond the LLM approaches AI for mathematics, including both mathematical discovery and also formalization. So we think that basically math is entering this period of promise and unease. There are a lot of AI-generated mathematical solutions, and a lot of them, sometimes in the middle, there's a bug somewhere. And I think because of that, people are trying to see what are some other methods that can try to be sure and have the trust that the AI proofs are correct. We also kind of feel like there's a lot of promise of AI and potentially exploring this sort of hybrid structure of both informal and formal reasoning could even like have more discovery and then you can verify this discovery. So it might the hybrid system might work better. So there's a lot of this sort of motivation going on. And in the old days, I remember, 3 years ago, the research math minutes like chalkballs and hero conversations, and then onto AGI, which is a big thing. In fact, mathematics has math missions before, so this is where we're now in the beginning. But in the early days, there's sort of automated reasoning community ATP, and they also have interactive therapy community where the interactive is basically about humans, and now interactive therapy extend to AI. Formal languages such as Lean and Rock and Isabel are gaining a lot of the traction. I heard a sound. I hope there's nothing changed in the speech. Um, Cool. So yeah, so basically, we want to see what are a lot of. I think AI for mathematics to us is a toolkit of various methods. Machine help in mathematics is not new, but there are potentially other ways to do AI for mathematics beyond sort of from the off-the-shelf provider large language models. And accidentally, we're doing some of these early explorations. So there's like kind of a transit mode. There's discovery where as a mathematician, we will have a lot of interesting ideas. A lot of them are not full-blown conjectures yet, so we will need to play with examples and patterns. We'll write out the first couple terms of the sequence, and then eventually we will start formulating a conjecture. So some people say that intuition is basically a lot of attempts and experiments from the draft paper to form pre-conjectures. And then there's the second mode of reasoning. A lot of the reasoning is done like humans in the natural language, and that is also the case of sort of LLM, literature search, informal proofs, proof sketches, hierarchical planning, as well as sort of the reinforcement learning, post-training regime with scaling reasoning. There are a lot of ways to scale search, both at training time and at inference time. And then finally, there's sort of verification, the formal statements, proof assistance, chat proofs, and reusable language. And because sort of there's three modes of these things, there probably should be three set of tools. So a lot of the kind of number two have been talked about, as in fact some previous speakers. I'm going to cover a little bit of sort of how we think about discovery and one verification. So the sort of model one is discovery. There is this paper back in 1974 called pattern boost, where basically constructing the manual examples was just a little help from AI. If for folks who are familiar with Android capacity sort of auto research ideas, you can actually try to automate the entire workflow of a mathematician in the sort of auto AI researcher way. But back then, when pattern boost was sort of proposed, it was still a lot of sort of human in the loop. So basically, we need to construct a lot of to have mathematicians look at the data, and then pattern boost is going to basically give you some subset of the data, and then you still need to look at the quality of that, and then basically generate new candidate objects, iterate, search, learn, search. So humans still can control a lot of the sort of examples and how they find whether it's still continue to iterate. And back then, it's a group of researchers, Dr. Charton, Jordan Ellenberg, and Anna Wagner, and Jody Williamson, they kind of like have this local search and global search concept of using a transformer, not the large one, to massage a lot of the graph data and then try to basically come up with new constructions. And that was a very sort of interesting toolkit for mathematicians. And with the help of discovery, they kind of had a lot of promising results that were state of the art. And specifically, there's this famous conjecture that's Graham Fahari conjecture, 1992, and patent boost actually proved it false. And that transformer is a decoder-only transformer, and it's actually just not so large. The counter example is just one with 81 edges. So not that this is all construction, not proofs. The interesting thing we're going to kind of talk about it in a bit is that what if you kind of merge these two workflows? Like you as a mathematician sometimes will do a lot of constructions, and after you have those constructions, you form a conjecture. And after you have a conjecture, you can then close it with a proof. And then you maybe looking at a proof, you will try to have other sort of directions, and then you go back to construction, and then you go back to conjecture, and then you go back to proof. So this sort of like workflow is something that we're trying to do. And I'm going to talk about sort of action examples of that. There's new thing coming out called Explorer. It's completely open source. You can download the code and just run it on your local computer. But essentially, then there's 2022 where we have large language models and chatbots are independent mathematicians, which is very familiar to all of us. I wouldn't go into more detail, but it was an inflection point. And there was suddenly, I think, the power of Prolong's paradox is really amazing. Just when the cost of reasoning goes down, there's a lot more sort of demand, and then there's also more supply, so the tools get more expensive, which is another interesting remark. But there these large language models like they master competition. So there's like the strawberry, OpenAI Google Meta IMO in 2025, as well as Google continuing on 2024 similar methods that Go Meta this year. Interestingly, for the first time, we have kind of like formal mathematics startup participate in math competitions. Harmonic kind of got a gold medal in the 2025 IMO. And we had actually got a perfect score on the Pundit exam, which the 2024 result was previously not reported by any company. So it's kind of, okay, well, we're now doing really, really well, humanity as a whole, on both on both high school and undergrad math competitions. And this reasoning kind of like breakthrough is quite, I think, spectacular in the sense that even for us, right, formal mathematics startups, they just sort of, you have a system of models, and then you will have basically post-train or open source based models that are largely formal models. So we have these sort of like very interesting timestamps from both really, really great benchmarks, such as Epoch AX benchmark frontier maths, pushing people to think beyond the sort of high school level Olympic math problems to first group, which are benchmarked by professional mathematicians, and they have made the New York Times, as well as a few other sort of like really great results. There's the Erdo human distance problem. It's a big breakthrough by OpenAI. Google DeepMind has Alicia, which is this sort of like agent that combines, and this Alicia was purely informal reasoning, but they also, I think, have the alpha proof nexus, which is sort of combining the evolutionary algorithm with some sort of half formal, half informal proof that isn't quite is similar to how we would do it. We try to basically collect research math problems from around the world, mathematicians, and then solve those problems for them, where the output are completely generated in Lean. And of that, we have also submitted some of these papers to peer-reviewed journals, and there are about a dozen papers that are currently accepted peer-reviewed journals. So it's an interesting sort of like time where we're seeing a renaissance of this stuff. And then there's this sort of formal verification world where, without AI, completely independent of AI, there is this formalization community that are having humans to, say, hard code undergraduate textbooks in method that's since 2019 by Kevin Butler and his students in Imperial College London. And what they were doing is they kind of start with like algebra. They found that algebra much easier to deal with than analysis, and then slowly, just like line by line, have these rewrites like dozens of undergrads to kind of build the infrastructure, all the definitions and important theorems and important lemmas in MATLAB, so that that's set out on this medical infrastructure for others to kind of build upon. The general, for those who are not familiar with formal verification, it is basically using formal languages that are largely type theory based. And you will have definitions, types, and then like types associated with each object, and then can convert natural language into formal language. So a lot of the sort of formal language programs first start with natural language proof. And proof as programs is the idea that is, it's not new. It's a correspondence. So there's a lot of gain about reasoning in natural language because it is flexible to present human, and a lot of gain also in formal language because you can basically have verifiable signals very easily, and you can also refactor things very easily, and you can also, without using large language model at all, use symbolic proof automation to close a lot of things. So formalization can expose the exact logical content of the idea. And Lean is one of our favorite formal languages because there's a lot of mathematical like mathematicians and Lean developers who love math, and it's a language with small twisted kernel. So Leo Deborah from was created Lean, like he was at Microsoft. I think this is about 2011, 2013, sort of like a history wrong, but Lean basically is a very widely recognized language, but it also has its cousins and sisters, and that's Rock, Isabel, Whole, etc. And you're also able to probably easily convert or fork some of the other formal languages into Lean with varying difficulty of how easy it is. There's also TPTP, the word of programming languages, where you can kind of try to convert between them. And Lean needs infrastructure. You want to be able to, for example, verify and prove in Lean a lot faster than, say, what the Lean FRO provides. And for that, there are community of people developing the Lean infrastructure, and Axo, which is also a set of free, like openly hosted tools that we pull out. You can use it for free with your favorite model, even some of the competitor models. Lean basically makes workings because it's able to kind of help us understand the details of proof in a way where, despite a lot of big results have been proven, in this case, spear hacking resolved by field medalist Mazovska, people still, a lot of, for students and a lot of other link developers and mathematicians, find it important to digitalize the proof, and in the process of digitalizing the proof, understand and sort of engage with the proof in a way that sort of reading it wouldn't necessarily give. And to give a little context of that, in selecting what are the sort of choices for defining things in this proof, in this result, you are basically grappling with multiple ways usually to define a certain term. And there are certain sort of trade-offs between these definitions. A single the term, the static object, can have maybe 5 definitions with different trade-offs. And if you choose, for example, the analytic way, you might suffer right now, and then for long term, it's a lot easier versus if you choose, say, the algebraic way of defining another theoretical object, then you might pay back later. So in the process of sort of playing out the game theory, the chess moves of how people would go about this formalization, it helps a lot of the link developers sort of in addition to digitalize the proof, they are able to basically understand and sort of make the proof a bit of a breathing object. There might be ways to even say optimize the proofs. So yeah, formalization makes work use. And this is like just an example of like action proving a theorem in Lean. The goal is to eliminate the sorry, which is sorry is something where it's like, hey, like take this statement as granted. And so to eliminate the stories to complete the proof, rather than sort of like take that as granted. And this graph I want to showcase is a dependency graph of verifying proof that's largely in the action system. So we will usually break the proof down in different states and then different basically sub problems that you need to solve. And sort of from left to right, this green node wouldn't be green unless all these sort of decomposition of proof states are marked as green, and then kind of goes down here. So for those of you who are familiar with, say, blueprints and large-scale formalization projects, in the past, because it is usually a collaborative effort, people who are like Carrie Dow or Tony Robbins, who do the prime and return end project, they will sort of try to break a big project into multiple parts, and these fractions of the project will then be delegated to lead tool users, developers, GitHub committers across the world so that they can focus on that local task. And then once that local task is more complete, people then can coordinate and like put the whole thing together. So it's a little bit similar to that spirit of decomposing, and humans, when they do a blueprint, is having a lot of advantage because they can basically turn mass that is usually an individual or say less practical collaboration effort into a big all-advanced effort, without necessarily requiring all the participants to have the same high-level understanding. You can just focus on the task in front of you. We find that in the AI system it works similarly well by decomposing it recursively, and then backtrack when necessary when you hit a dead end. You are able to basically decompose pretty scary ambitious goal into multiple, much smaller sub goals, and then in the end, you might actually have a chance of having one shot zero tuning models that are much, say, smaller, maybe on the orders of tens of billions, instead of much larger models to close out those living tasks. So we're going to like see more of these graphs in the future, so I wanted to provide some records of context. So Maslin, which I can mention briefly, is that this sort of shared mathematical infrastructure, in addition to Lean, the infrastructure, the relationship between Lean and Maslin is a little bit like Python and PyTorch. So I mean, this is like the largest library, and it's a library of mathematics. There are other libraries such as CSLib. We at Axiom is developing some other libraries, other domains. And there's also, for example, the ZK proof, the zero knowledge proof community. They have their sort of like library as well. And it's very, very important that some critical dependent things are in Maslin because the AI's ability to say introduce new definitions into an existing knowledge base and make sure that it doesn't fight with all the other stuff that's already in there, which in the computer science terms called library learning is currently not very good. So if you do not have something that's critical, say an L function is not defined in Maslin, then doing anything related to the L function is going to be challenging. So a lot of people are basically doing volunteering work for the Maslin initiative, and they're really doing really good work. So formal verification also has a lot of real-world applications, such as software, hardware verification, security, and other AI for science applications in say, biology and stuff. It's basically sort of a good proxy for a sandbox for trustworthy. And so we kind of talked about this very much, and I want to give a little bit of examples of each of the nodes here at Axiom, and maybe hopefully some of these tools and software we put out could encourage people in the TCS community to use them, because we so far have been solving a wide variety of math problems, but a lot of the theoretic computer science problems could potentially be attempted as well. So discovery, there's Explorer, which is again on our website you can find this entire code base, and you can just download that GitHub. So the version of having boost found the backbone solution on the 404 cycle problem for annual 33 nodes. But that was like a lot more expensive. The whole thing about Explorer is that there's a huge efficiency gain. And in fact, you do not need like Evolve or like Google supercomputer to do these sort of mathematical discovery. Mathematicians can download our code and run it on your MacBook that hopefully has at least one GPU. And this is basically a way by kind of doing a lot of system level work, such as like, doing a lot of sort of tuning of on the temperature and then try to have sparse encoding on the trick to make it a lot more efficient. So basically the Explorer was able to match pattern rules on all the problems that it solved with just a fraction of compute resources and a fraction of the time. So we kind of jokingly say that give me $3 and I will give you a state of the art of the short 4 seconds problem. It's kind of becoming a reality. With this sort of Explorer sort of idea, we also have something that's rolling out on XSolver. The GitHub is already up. It's also open source code using the XSolver, which is a translated method for discovery. So if you have a lot of problem and solution pairs and you want to predict the next solution from the next problem, then you will use XSolver instead of, say, using Explorer to do construction. So it's generated methods versus translated methods. And a lot of people who want to predict sequences will use XSolver. So for example, they are trying to use XSolver to predict the cola sequences. And that is actually something that shed light to the machine interpretability line of research. There are also a lot of physicists using the XSolver to say predict the amplitude of in things like in Young theory, and there are a lot of successes across the sort of applied math and science fields by XSolver that is much more efficient and optimized version than Instrument. And these are work done by François Charton and Robert Carina through FC. Okay, so the two recent things is that since February 1st, we have rolled out Improver as a bit of a research mathematics tool. We have written end-to-end Improver some papers and also some other papers that we need to talk about for number case study number 3, which is human AI collaborative efforts. Out of this 11 papers, 7 are accepted for peer-reviewed publications. These are examples of formals they're improving. You can see that they span across number theory, algebraic geometry, representation theory, and combinatorics. I'm going to kind of go deep into these 2 examples. The one example is that there is this very well studied sort of like problem in algebraic number theory, is that for sort of the P part of the plus grid CLKP, you will have like you can decompose it into a certain sort of like hierarchy of eigenspaces, and humanity is for everything. And for all the odd parts of humanity as a whole understood it very well. This is the famous Herbrand-Ribet theorem, and we know exactly about when the odd parts vanish. On the other hand, there's nothing known about the even eigenspaces. So all the ones indexed 2, 4, etc. are not known. And this is a very old conjecture, almost 100 years ago, by Thomas and Vandenberg, saying that having certain sort of guesses about the even conjectures. Sorry, the even eigenspaces. Now, what we were able, we in action proof, were able to prove is this main theorem is that for almost every prime P, so 100% of the primes, you will have a big part of these even eigenspaces to be vanishing. And this paper is accepted by our Carina mathematics. It is an interesting result in that it is the first sort of infinite theorem that we know about the even eigenspaces. So this is an example in algebraic number theory. Here's another example, sort of a little bit more analytic number theory flavor. So the Ramanujan-Tau function, which is the very famous number theoretic object, and it's the Fourier coefficient of the modular discriminant delta. And it's sort of like it existed in Ramanujan's like lost notebooks for many, many times. People really don't understand this Ramanujan-Tau function. So here's like kind of its absolute value distribution. There is the question by Lieber about whether it will ever be 0. It is a good problem. Other people will ask questions like when is the Ramanujan-Tau function prime? Basically, Axel will show that assuming the HC conjecture, which is a classical kind of assumption in number theory, you can actually show that the Ramanujan-Tau function misses 100% of the primes because of the following asymptotics. And this is another example of we do not know for all primes whether it misses all primes, but it misses 100% of primes. And the proof is also quite sort of quite a little bit more combinatorial, and then this is also down the output is end-to-end down. And this is the proof graph of the Ramanujan-Tau function. And this is about 500 reasoning nodes. It's thousands of lines compared to, say, the earlier problem 124, which we kind of like amount that we managed to resolve in December, that turns out was already solved before. But this is an example of like 50 reasoning nodes, and it's scaling from 50 to 500. We're going to have like see larger and larger graphs, and even just very very large graphs for a very very small part of the proof. It's we're trying to scale this with not necessarily a clear. And the last bit, which I'm going to be quick, because time is running out, is formalization. So if you are a super mathematician, you have a preprint, or you just have a very, very rough outline of the proof, and you're like kind of lazy, or maybe you're kind of sort of skeptical of that. There's this famous anecdote about how Americans of Kanye was always very skeptical of whether the big proof was all correct or not, and might have nightmares over that. Yes, as a mathematician, you always have that sort of worry, concerns. And this is an example where we study sort of the weak surfaces relating to dynamical systems, and it is in the research direction by Marion. There's a portion by Alex Wright, a professor at Michigan, and they kind of like have this sort of like open problem, and this open problem was actually sort of Ken, who's our in-house mathematician under series, has an idea, not like they how to do it, but do not really know the technical details enough to say complete enough. And in this case, we were able to have Accent Cooler show this proof sketch and then basically make corrections, optimize it, given the details, and produce a whole lean 4.26.0 formalization all of the proof. And this resulted in a paper on the paucity of lattice parameters. And this is like an example of like, okay, well, I actually do not know how to prove this per se, but I have like a rough idea, intuition, and then because of formalization, you can trust that the final proof when actually produced and linked is soundproof. This is another example in sort of combinatorics. There's this preprint by Yifeng Wang, and we were able to take that rough preprint and basically convert that into an end-to-end lean auto-formalization, showcasing the auto-formalization ability is actually not necessarily easier than proof because the graph and the sort of reasoning that the system needs to do is also quite significant. And this we write it as an appendix in this paper by Yifeng Huang. It's accepted by a peer-reviewed journal. The review process was significantly sped up because of lean formalization proof provided alongside the paper. This is also why we were able to get so many papers peer-reviewed in a short amount of time. And sort of like their directions next, and I also know that I'm really out of time, but basically we are at the beginning of research explorations and conjecture. We have examples, working examples of AI-generated conjectures through an informal formal hybrid approach, as well as better library. We also believe that formal proving scheme has not been fully harvested. Matching informal AI systems on mass linkage is just the first step. Matching the results of the research experiment, which is not now because there is much more milestone and also more result, and this is something that we're working toward. And there are low-hanging through and high-hanging through, such as symbolic proof automation that's specific to the formal languages, as well as sort of like AlphaZero like style, like asymmetric template that we are exploring and trying to make sure that our partisan collapse. We want to integrate AI for discovery literature together with the informal sort of reasoning together with the formal verification, and all three really should be a loop, and it should be a self-improving loop of endless conjectures being generated, proof being completed, and then new constructions leading to new conjectures. We have a few of these examples working, but they're not necessarily very sophisticated and breaks the result. We want to kind of like bridge that gap and bring this workflow to the world, showcasing that related example. And finally, my last slide is that we're doing e-column, which is a lot of the auction series and game series. They're like trying to formalize microeconomics, which has a lot of math theory using Lee. And in doing so, one of the initial project is to formalize Robert Ullman, the Nobel Prize winning economist, sort of agreed to disagree result. It is a famous result taught for 50 years in Econ 101. Turns out that there is a big part of it that's an implicit assumption, never made explicit, and that is what the Accent Cooler realized in the formalization, and we were able to then use Accent Cooler to patch that. So there's a new paper written together with Scott Commoners from Harvard Business School, and a lot of economists are quite excited about it. We're doing another project quantum computing, and we're doing another project in sort of deep learning theory. We're very excited about whether the sort of TCS community would like to say maybe have like large scale formalization of classic TCS results. Thanks so much.
Thank you so much. Yeah, thank you so much. Are there questions?
Do you use any frontier models in your proofs?
Oh, wait, her voice. Sorry, sorry. Oh, wait, sorry, something has happened. Your audio has gone out. Just a second.
Right. So Action Brewer is a system of multiple models, and most of the models are post-trained on open source based models like the ones that everyone's using, and then similar sort of intense RL for coding post-training is applied in those open source models. In a very rare case, we have an orchestrator actually to kind of control a bunch of different things. And we're basically experimenting whether a model can do harness. So, and this cost being a consideration. So I think it's like if the system is designed to be plug and play, and lots of results are thanks to the really good sort of like advances in I think post training and to generate building code.
Any other questions? I had one question, which is that like the lean version keeps getting updated in Mathlib.
Yes.
Oh, sorry. Okay, so there's another question, so let me go to that first.
There's been a lot of concern given the recent story of auto-formalization project that completed a master's student's project in 5 days. Do you have any comments on the concerns about that, especially in regards to the ability for students to be able to find projects that won't be completed by AI auto-formalization tools?
Yeah, it's a great question. In fact, I think Sid, who leads the spearheading, one of the beginners of the spearheading projects. Currently, I have him doing the summer internship, and I think he's also participating in other auto-formalization projects that we are doing. We find that responsible auto-formalization takes time if you really have a lot of demands of the code quality of the output to be in a way not necessarily backlit quality, but as human understandable, easy for human developers to build on top of it instead of sort of more sloppy code. We do not believe that the speed in that specific case of that competitor Taiwan is going to apply. I think that the experience of us doing large-scale formalization projects is that if you want to have responsible output, actually take not only just the AI, but also a lot of, I think, human sort of participation in the loop. So I think there is still, at least today, a lot of like room for people who are interested in formalization to do projects, engaging with more and more, I think, like systems, AI systems with good formal proving and other formalizations that are correlated capabilities. On the sort of broader question of like what this is going to impact, like sort of student selection of projects, is that I would say practically there's still a huge amount of stuff that's not in Mathway. I know that a lot of great institutions and like Heather, for example, is trying to do like differential topology and other geometry and like all these stuff and put it in the infrastructure massive. And I think that those are a lot of areas that can be done by students.
Thanks, Carina. I had a question. So, as someone doing this ambitious work in the industry, what do you think are the direct applications of theorem proving towards that you could commercialize?
Yeah. So this is a very interesting question because we actually have been discovering this. I think not at this. We didn't have a good answer at the start of the company, but throughout the course, we realized that formal theorem proving capability transfers very well for formal verification use cases in the real world. specifically code verification, where say code can be hardware system verilog code. Code can also be, say, various programming languages, even though I could say there's a hierarchy of programming languages, there's some are obviously a lot easier than the others. Like, use a formal language to verify something that's like statically typed. It's probably a lot easier than those dynamically typed programming languages. And we are exploring a lot of these sort of applications in both the hardware and the software as well as security spaces. In addition to formally proving things, we finding counterexamples that is a correlated capability is also very crucial, because in the real world you have security programs that have some bugs, and if you can find certain bugs and patch it, then it's going to be hugely beneficial to those like customers or partners, as well as in the smart contracts work, people actually have bug bounty, so that tells us things like the flip side of proving, which is finding bugs and fixing it, is going to be quite valuable. The last part I would say is that we have instances where through trying to formally verify a large program, we're able to compactify the program by a significant amount. So like in math, if you have an instant proving thing, you can then massage the research problem quite a bit. You can tweak this assumption, and you can loosen that, like bound. You can try to basically massage the problem. Like, it just becomes like a living, breathing object rather than like a fixed one. And that is the sort of verification generation or verification design loop that we're seeing. So if you have a hardware and then you want us to verify the hardware, the chances are you have better design from that. So it's going to slowly become a more end-to-end kind of like vertical application. And this is the same as, say, like certain software programs as well.
I have a question. So you mentioned library learning as a direction. So it is in the sense of like a program comparison, abstraction learning, or it is for lemma creation, lemma search. So could you elaborate on this library learning a little bit?
Yeah, so library learning, we really find like definitions a little bit difficult and tricky to deal with. So if you want to auto formalize, you want to drive up the accuracy of formalization, you want to say try to work on things like canonicalization, which is like to basically have the same human judgment and haste as those massive people were like Sid when he's starting to formalize the spear packing project, like what definitions to choose and what are the long-term, short-term considerations. And even I remember there's this complex analysis choice of like which contour do you choose. If you want to have that in your AI or formalization system, it becomes difficult. In fact, I would say that conjecturing is a lot easier than library learning. But what we found is that we have ways to basically have AI generate good informal and formal conjectures, but we don't necessarily have very, let's say, clear short-term solution for library learning. It is about the definitions of that anonymous, and you have a lot of ways to sort of measure usefulness of things. If you want to measure a conjecture being useful, it's actually you can like consider how many new things it's going to bring, etc. But for definitions, it's a lot harder, I think, to do these metrics and do it all.
Hi. Thank you for your talk. So you mentioned as application formal verification of code, but it turns out that Lean is quite limited in that respect, like especially like if you care about efficient extractions of the code. So are you considering using other technologies like ROC?
Yeah, that's a good question. A lot of the software verification works in Dom and Rock, for example. You basically are seeing a lot of the formal languages potentially being good choices for one thing or another. And the good things, however, is we believe at least that there are ways that can promisingly convert from say Rock to Lean. It's one of our resident projects this summer actually. So over 3 months time, we have a really wonderful person researcher. Who used to have his PhD thesis converted deductively to now convert say Rock to Lean. I think the point about like which formal language to use is a tricky question because it is also possible that you might want to create new abstractions or like maybe another sort of formal language that's going to be most suitable from a performance bottleneck standpoint of the verification. So far what we are doing is we are seeing transfer learning from like one formal to another. We are seeing the sort of possibility of having, let's say, GHG inverse, G specific for each like sector, and then H is sort of like from link-based verification conditions to generate improved bias improvers. The H is shared, where G can be similar for hardware things, G can be similar for some particular kind of software things to do this sort of layout go to market.
Thank you for the talk. For some part at the end, I think you mentioned something about maybe using asymmetric self-play as like a high-hanging fruit. I was wondering like what you think this might look like in the future. I know, like for example, AlphaZero was able to find like theory that like or like have a deeper understanding of chess than the humans can like, put into words. So if that happens for math, like A, what do you think would be the path towards that, and B, like how do you think we could distill that like deeper understanding to humans?
Yeah, that's a great question. So we so far are seeing it being a mostly an engineering problem. The one thing we're battling is your training actually does work. So that's kind of what we are at the stage that we're at, and we have seen some like sort of promising runs where we believe that this can be scaled a bit more. Because we're still at this stage, I haven't really had the time to consider what will be the outcome of that. What the one thing that sort of is good about this approach is that you basically are. Can you hear me? Oh, you basically are able to kind of just asymmetric stuff. You can just kind of keep going and start from there. I haven't thought about. Yeah, I really haven't thought about what happens, and I also don't know. Like, it's a bit hard to define, understand theory, just from my perspective, because it's just like it's hard to define reasoning. It's very, I think all the sort of eval and benchmark side actually from a machine learning standpoint lags behind, say even how to measure say the quality of formalization, and not to even measure the quality of conjectures, or to measure the qualities of understanding theory. So I think because we are so eval and benchmark bound, it's hard to define some of these questions.
Yeah, okay. Yeah, let's thank Carina again.
Thank you. Thank you.